Now this one's kind of a fun application of what we've been looking at, and it deals with positions and a position function. Basically talks about how far is an object off the ground or off of some object given certain time. Because we know every time we throw something up, it's going to come back down. And over time, we could graph that position on a quadratic curve. So imagine that because we like to do it, we like to go to tall buildings and throw rocks off of it into a safe spot where nobody's around. Well, we can model that, and typically how we model that position function is by this equation where the position as a function of time is determined by -16, which is the acceleration constant, times t squared, plus initial velocity times time, plus an initial starting position. So you take those three considerations into place. Where do you start at? How fast do you throw it? And then the effects of gravity. Put all those into an equation and we get this position function. So here we are visiting someplace over in Europe, come to a nice building that's just not quite leaning straight up. We climb to the top, bring a rock with us, and we want to toss it off. So we're curious of lots of things. One thing that we might be curious of is, well, if I throw this rock way up and then let it go down, I might be curious for how long is that rock going to be above my position. So let's say that the position where I throw the rock at is 190 feet up. I want to know for how long is this rock going to be above my position before it starts to fall and starts to get below 190 feet. Of course, there's other questions we can ask, and you can solve other ones as well. The initial conditions I know is that I'm starting at 190 feet, and I've got a good arm. I'm throwing at 96 feet per second. You'll see why here in a second. So how do we solve this? How do we know for what amounts of time will this object be above my starting position? So we have an inequality forming. I'm asking for what positions is this function greater than or equal to 190 feet? Because this function represents the position at any moment. And I want to know at what time is it going to be greater than 190 feet. Of course, we can ask the other way around and find out for what moments on the other end. But we just chose this first one to start with. So how do we solve this? Well, first of all, let's set it equal to 0 to figure out what our boundary points are. So I start off with, I'm going to rewrite it around, 190. Subtract 190 from both sides. I'll have 0 less than or equal to -16 squared plus 96t. 190's go away. I'll multiply both sides by a negative 1. That flips the sign around, but I'm still interested just only in the boundary point, so I'm not so much worried about that. So that's going to give me a 16t squared minus a 96t. Again, we're looking for boundary points. We're looking for where it's equal to 0. Later, I'm going to come to the inequality and decide for which values is it true. So this being the case, 0 is going to equal 16. I can factor 16 out. I can factor 16t out. And I'm left with a t minus a 6. So this is true either at 16t equals 0 or t minus 6 equals 0. And that's true at t equals 0 and t equals 6. So there's my boundary points. So we can do what we've done in the past. Graph out a line. We know we have a boundary at 0. I'll make that a 0, but that's also one of my boundary positions, and also at 6. So I have 3 sections we can explore. We have from negative infinity to 0. We have 0 to 6. And we have 6 to positive infinity. Now, notice a couple of things here to begin with. What do you notice? Well, because we're dealing with an application, we have to be aware of model breakdown. Do times before 0 make sense in this model? No. So we don't really need to check those because a negative time in this model doesn't make sense. Graphically, we can represent that because this graph, if we started here and worked way backwards, we can graph the negative time scale of that, but in reality, we haven't figured out a way to actually back up time yet. Unless Dr. Strange is around, then maybe he can help. Then 0 to 6 is the next boundary point, and there's a time 6 afterwards. And there we got to be careful too, because this graph at some point is not going to go out for infinity. Time's not going to go forever. This rock's eventually going to hit the ground. That's something else we can deal with later. But for right now, we're just curious about what happens between 0 and 6. And so let's find out if that's actually true. We think it is, but let's find out if it's true. Let's choose a test point, like maybe 3. Put that, well, that's an ugly number. Let's try 1. 1's a better number. So if that's being the case, then I'll do down here. So 190 is less than or equal to negative 16 times 1 squared plus 96 times 1 plus 190. I subtract 190 from both sides, which is fine. I'm just going to reduce it first. So then I have 0 is less than or equal to negative 16 plus a 96. Add those together, 0. I don't know what that is. That's 80. Is 0 less than or equal to 80? That is true. So that tells me for this equation to be true, my solutions of where the value or where my object is greater than my height at 190 feet happens within this time frame right here. And since it's equal to it, also includes 0 and 6. So my solution set are at times from 0 to 6. So for the first 6 seconds, I'm going to be able to look at that object above me until it gets right at my spot. Then after 6 seconds, it starts to fall down. The question we ask later is, well, when does it hit the ground? How much time does that happen? And I think you guys have enough skills to find that out if you're interested. Or just go to the building itself and time it.